Good afternoon. Let's see if I can pass the slides. Great. So one of the main goals of the ARTEMIS program is to understand the character and origin of lunar pole volatiles. And one of the main challenges to do that has to do with sample collection and their return to Earth, because some volatiles are very sensitive to temperature, so they have to be stored under very cold conditions. And other volatiles, which are associated with phases and are stable at ambient conditions, will react with the Earth's atmosphere. So samples need to be sealed and stored and processed under nitrogen environments. One example of a volatile-rich sample is the Apollo sample 66095, also called Rusty Rock. This sample was collected at the Kailai Plains by the Apollo 16 mission, and it has a wide variety of lithic clasts, from basalt to anorthosite, with a wide variety of mineralogy. And its main characteristic is that it has abundant evidence of alteration. And here on the left, you can see an original examination by the crew, 1962, where you can see that there's metallic salts or rust on the surface of the sample. I'm also showing some TM images of chlorine-rich iron oxide grains with these rod morphologies. However, the origin of this alteration has been debated for decades. It's not clear whether these occur on the moon or if this is associated with some extralunar processes. So the goals of this study are basically two. First, to clarify the origin of the alteration of the volatile-rich phases in 66095, and then to design a new methodology to extract mineralogic and crystallographic data from sealed samples. So the research questions are very straightforward. What's the origin of the volatile enrichments in 66095? For example, is the oxyhydration a product of terrestrial alteration of lunar chlorides like lawrencite and iron nickel metal to acarenite, or does it come from indigenous lunar processes? And to what extent the alteration, the rust, penetrates the sample? The outline of the experiment is below. Here we see that first we've done micro X-ray computed tomography imaging of sealed samples at NASA Johnson Space Center. Then 3 subsamples that were less than 2 millimeters in size were placed in pristine nitrogen atmosphere in sealed gas containers, and then also covered in Teflon bags and at the NASA Johnson Space Center, and were sent to Barcelona, where we have analyzed these sealed samples by micro X-ray diffraction at the synchrotron ALBA in Spain. And then the gas containers were punctured and exposed to terrestrial atmosphere for 2 months. And finally, repetition of the analysis at the ALBA synchrotron will observe alteration phases with the terrestrial atmosphere. So far, we've done the first 3 steps, and we are currently at the 4th step, where we just puncture the container caps, and we are waiting for the terrestrial alteration to occur on the sample. So in this talk, I'm going to show these first 3 steps. The XCT scans of the samples are here, and you can see that the rust, these metallic grains, penetrate the sample. They are clearly observed into the grains of these sealed samples that were selected for study. These 3 subsamples were extracted from 436 and were kept in pristine nitrogen atmosphere. And then the glass vials where we placed them were first sent to the cleaning facility of the NASA Johnson Space Center to be cleaned by ultra-pure water, dried, and placed under nitrogen for 2 weeks prior to placing them, and then also cover them in 3 Teflon bags and sent to Barcelona. In Barcelona, we wrote a proposal to study these 3 samples at the ALBA synchrotron light facility. And in order to get the proposal accepted by the material science powder diffraction beamline, we also ran a preliminary test on April, where we wanted to make sure that the sample was diffracting well, despite being inside a glass container. We did see that it was very well diffracting, but we observed that the peaks were matching very well, were fitting very well at the center of the diffractogram. However, they were stretching at the opposite directions, at the edges of the diffractogram, due to the glass. This was the contribution from the glass. So in order to correct this effect, we did a new calibration where we placed lanthanum hexaboride grain into an empty vial to measure how the glass was affecting the shift of the peaks. And then we corrected for the experiment, for the actual day of the experiment, we corrected this measurement. We also designed a support that perfectly holds the glass vial using a 3D print. The day of the experiment was in July 13, and we mapped the 3 grains by taking an analysis every 15 microns and having the 3 maps completely covered, the 3 grains completely mapped. So we had 1,200 spectra to each sample and a total of 3,600 spectra for the 3 of them. The results are not processed yet, but here I'm showing an example with 20 spectra on top. And below, I put reference minerals from known mineralogy of this sample by previous studies to compare and to show how we will analyze this spectra. So now I'm going to zoom in into this same diffractogram to show it better. On the left, we see that the peaks are matching well with anorthite and forsterite, and maybe we have some lawrencite and troilite and some unidentified peaks. And then we also see that there's no presence of goethite or kyanite. In the middle of the diffractogram, we see that there's very well matching with anorthite, forsterite, and troilite. There's no hematite or goethite, and maybe there's a kagenite and sphalerite and unidentified peaks as well. And finally, on the right side of the diagram, of the diffractogram, we can see again anorthite, forsterite, troilite. There's no goethite or hematite, and we may have lawrencite and unidentified peaks. So what can we say so far? So far, we have demonstrated that micro-XCT imaging is capable of characterizing lunar bore volatiles, without alteration. We could see that the RAS was penetrating the sample. We also have demonstrated that X-ray diffraction measurements can be made on sealed samples within X-ray transparent containers with nitrogen atmospheres. And even though the results are not processed yet, we already see that there's a very good match for anorthite, olivine, troilite, lawrencite, and kamacite. We have demonstrated that volatile-rich lunar samples then can be successfully analyzed and imaged without terrestrial contamination. And more importantly, with synchrotron micro-X-ray diffraction, we can identify specific mineralogy of a sealed sample. What's next? We are now letting the samples to interact with the terrestrial atmosphere. And then in September of this year, 2024, we will repeat the analysis to observe or to study the alteration products. This will be examined by TEM at Goethe University in Frankfurt next year. And finally, we will be able to discern between lunar or terrestrial alteration in 66095 and the origin of the rust. Thank you.